Hello, hello, hello. Am I audible? And are you able to see my screen as well?
Yes, sir.
Okay, fine. So, hi, good evening.
Good evening, sir.
So, how is it going?
Fine, sir.
Okay, so we are about to end this course in next 2 or 3 lectures. And before that, I mean, you are consistent. So, I just wanted to ask you that do you want anything to cover up in the next class or anything so that we can have it before ending this course? Okay, if you come across any topic which there is a need to cover up before the ending of this course, then please mail me or write in the Q&A box in on NPTEL. I will take that into consideration and try to incorporate that into the further class. Uh, Now we'll just wait for a couple of 2, 3 more minutes. We'll start this lecture at 6:05. So if others wants to join, they can join as well. Yeah. If you have
Okay,
anything,
sir.
yeah, if you have anything to ask, you can unmute and ask. Okay, I think we can start now. So hello everyone, welcome to this problem solving session of NPTEL on course of Geographic Information System. And I am Hiren Solanki, going to conduct this session. So I am a PhD scholar at Department of Earth Science at IIT Gandhinagar, and I work in the area of machine learning and hydrology for flood inundation mapping and flood forecasting. So with this, I think we'll start this session. So as we do in the all other sessions, first we'll start with taking some quiz from the video lectures from week 11. So basically solving different types of questions. Then after we will go and check some of the websites, exploring the data sets from various websites. And then after, at the end, we will go and do some of the practical hands-on session in the QGIS. So with this, let's start the session and with our quiz for the previous class. Okay, so yeah. So week 11 was on the various kind of derivatives which we get from DEM. And then after this week also focus on some of the capability of GIS for hydrological analysis, specifically the catchment area delineation, watershed, dam inundations, and so on and so forth. So today we will solve some questions based on that, learn about contours, and then after we'll see some of the applications in the hydrology as well. So basically this course till now we have finished till week number 10, and this particular week 11 is focusing on the various DM derivatives part 4, then some of the shaded relief models and their applications, DM based surface hydrological modeling, so that is in two part, and then after we have dam simulation and the applications in the groundwater hydrology. Okay, so starting with the questions, our first question is: a digital elevation model is best defined as vector representation of terrain, raster representation of a continuous surface, discrete representation of elevation points, aerial photograph of terrain. So what should be the answer?
Option B, sir.
Yes, so DM is a raster, or we can say the continuous representation of a surface basically. So that is correct. So both vector representation is a discrete one and it's not a continuous. Similarly, here we have raster data. So like point is again a vector format. So C is also wrong here. An aerial photograph of a terrain. So it's not a photo, but it's just having some values. In photo, we have three different bands or one bands which is giving the reflectance. But here elevation model will give us the value of the pixel showing the elevation of a particular location. Next question is: DEM or digital elevation model represents the real world terrain exactly at 1 to the 1 scale or 1 to the 1 ratio. Is it true or false?
False, sir.
Yes. So DM, if we'll show as a 1 by 1 scale, there is no meaning of doing it. Basically, we want to cover a large area and want to get the overall topography on a single sheet or single map, and that's why we reduce the scale in such a way that we represent 1 meter on a real ground is like basically 1 meter on a map is equivalent to 50 units on uh, actual world or similar to. Basically, we reduce the scale so that we can uh, represent a larger area into a smaller dimensions. Similarly, if something is big or something is changing a lot, then in that case we can like increase the or decrease the scale also, presenting the enlarged view or enlarged magnified view as well. Next question is: in a DEM of 100-meter resolution, one pixel represents how much area? 10 hectare, 10,000 meters square, 1,000 meters square, or 1 hectare?
Option B, sir.
Yes, so here you have to focus on there are two units given, meter square and hectare. So first of all, you should know what is the relationship between meter square and hectare. How many meter square is equivalent to how many hectare? Because otherwise, more than one option can also be correct. Okay, so if you see that hectare to meter square, so 1 hectare is equal to 10,000 square meter. Okay, so according to that information, is there any other option which you can think of here?
Option D, sir.
Okay, so there are two options. do the unit conversions, and according to that, the option number D and B both are correct here. Next question is, which of the following is not a characteristic of DEM? Continuous data, raster structure, discrete elevation representation, or abstract model of reality?
Option C, sir.
Exactly, because DEM is a continuous data, and that's why the discrete option is wrong. Discrete can be useful when we have contour points and we want to show the elevation. But in case of DEM, generally, like we want to show elevation of particular location, basically, then we use the discrete values. But in general, DEM we represent using the raster, which is a continuous data, and as like it's not real, so it's abstract model of the reality. Is option A, B, and C. All three are correct, whereas option C, discrete elevation representation, is wrong. Next question is, the primary reason DEM is considered a model is it uses the vector data, it generalizes terrain into grid cells, it stores multiple elevation values per cell, it's always 3D.
Option B, sir.
Yes, so it generalizes the terrain into grid cells with the pixel values which can go for positive or negative both, depending on how much elevation is changing. So option B is right. It's not a, it uses vector data, that is wrong because it's a raster data. It stores multiple elevation value per cell, so that is also wrong. It shares the one single value, which is the average elevation of the particular grid. It's always in 3D, so that is not correct. It's in 2D format only. The value in the pixel is, if we extend it, then it can be a 3D, or we can, if we represent it as a 3D. Next question is, closely spaced contour lines indicates gentle slope, steep slope, flat terrain, or plateau.
Option B, sir.
Yes. So if contour lines are near to each other, then it represents the steep slope. So I think in the after finishing these questions, we'll also look into the characteristics of the contours briefly, so that you will get more idea using the DME of any location. The next question is, in rugged terrain, DM error increases because of pixel size decreases, elevation variability is averaged out, DM stores vector data, or resolution increases.
Option B, sir.
Yes, so variability is high between the elevation of nearby pixel values, and because of that, ruggedness is generated. Which of the following is considered as a discrete data? DM, tin, contours, or raster grid?
Option C, sir.
Yeah, so contour is a discrete data. DM is a continuous data represented by the square pixels, and overall DM can be rectangular or square. Tin uses the concept of triangular irregular network, which is represented by the triangular faces, which is having edge, node, and face kind of structure. And then, which is also continuous one, contours, which is a line joining the equal elevation, and which can be a discrete data because it will created using the contour interval, and at that particular interval only we will have a line which is enclosed. Apart from that, we do not have anything which is not continuous. In the raster grid, it's already continuous data sets. So correct answer here is contours. Next question. Widely spaced contour lines represents steep slope, gentle slope, cliff, or ridge.
Option B, sir.
Yes, so if it's densely spaced, then it represents the steep slope. If it is a widely spaced, then it represents the gentle slope. And if it is overlapping something like on other contours, then it is represented by cliff. And I think we'll just see an example of how the cliff contour look like. So if you have cliff, then the contour line is similar to this. So if you have this kind of structure, let's say if you have this kind of structure which is overhanging cliff, then in that case, see here if this elevation is equal, so we'll get a contour in corresponding to that. But at the same location, if we see basically here, then we have one elevation at this location also and the same elevation at here also. So we'll get two elevation value at a single point, and that's why the contour line will cross each other. And because of that, in this particular case, in the case of overhanging cliff, the contour lines crosses each other, and which is like opposite to its characteristics. Okay, moving to the next question. Contours are continuous data, true or false?
False.
False.
Yes, the contour is a discrete data set. Next question is conversion from DM to contour represents which kind of operation? Vector to raster, continuous to discrete, discrete to continuous, or raster to raster?
Option B, sir.
Exactly. So we have DM, which is a continuous in nature, that we are converting into contour, which is a discrete in nature. So it's a continuous to discrete operation. Next question is which parameter is essential for contour generation? Pixel size, contour interval, projection, or color scheme?
Option B, sir.
Yes, so we need a contour interval at which particular interval we need our contour lines to be drawn in. Pixel size do not matter here because we are dealing with the vertical accuracy. Like it may reduce some of the accuracy in the like vertical dimension, but yeah, overall in generation it will not create an error. It will be issue of accuracy, not the generation part. Similarly, in whatever projection system do you have, you just have to see line joining the equal elevation. So you do not have to think about the horizontal dimension or the two like XY dimensions. So that's why projection will also not affect whether it's in degree or meter. But for surety, it should be in a meter so that it will look proper, not distorted one. And then the next one is the color scheme. So that is just for visualization purpose. That will not affect anything to generation part. Yeah. Moving to the next question. Maximum precision of contour interval depends on spatial resolution, vertical resolution, which is Z unit, map scale, or projection.
Option B.
Yes, so basically the vertical resolution. And why is like if you have contour data with you, or let's say you have DEM, which has the accuracy of let's say you have just 1 meter, 2 meter, 3 meter, 4 meter, like that you have recorded the elevation values. So obviously when you will go for generating a contour, maximum contour that you can have is like 1, 2, 3, like which are highly precise. Even contour, it's line joining equal elevation again. So what we need to do is we need to just do the interpolation. So it's not like I cannot generate a contour at 0.5 meter or 1.5 meter, but the accuracy will not be that much. Okay, so because of that, like it depends on what vertical resolution do you have in your data. So basically, generally, most of the DM which we use, they have an error of 2 to 3 meter in a Z. Because of that, that much error we are getting. Next question. Which of the following is not true about contour lines? They form closed loops. They never cross each other. They form closed loop in all maps without considering the map boundary. Irregular contours indicate uneven surface.
Option B, sir.
They never cross each other. So, yeah, in general, it's true, but yeah, like it happens when we have just a physical barrier such as overhanging cliff. But that statement is like, I guess it's true, but like you have some of the exceptions. But in general, this statement is true that contours never cross each other unless and until it's a overhanging cliff. So I think we can consider that this is as a in general statement is true. But if we consider the like example of cliff, then this becomes unvalid. But yeah, can you think of any other options?
Option C, sir.
Exactly. So they form closed loop in all maps without considering the map boundary. So that is not true. Why? Because if you are considering a map of some of the area and if it does not have same elevation of 500 meter, it's just ending in the some another map or some another tile. So you will not get your contour lines closed. It will be open only, but in other panel, it is going to be closed so that we are not able to visualize. So it doesn't like like if you're considering full part, then it will close. But yeah, if you are considering a part of it, then it's highly possible that it will not close. So it considers the map boundary only. If you are considering the representing some particular area, then the contour lines might not close also. But eventually, if you extend that map, you will see that closing of the contour lines. So option C is correct here, like which is not true about the contour lines. It considers the map boundary, and according to that, it closes or becomes open. An irregular contour indicates uneven. That is also true. So that's it. Next question is contours can be derived at finer intervals than the source contour data. True or false?
True.
Yes, the answer is true only. Why? Uh, because like we contours are just we have to do the interpolation in between. So that's why it's true only because like if I have 1 meter accuracy, I can interpolate between 1 meter contour interval and 2 meter contour interval. I will get a point 0.5 data sets. So that's why like I can go beyond it also like the whatever vertical resolution which I have, but the precision will affect accordingly and accuracy as well. Next question is which application uses single contour extraction? Flood modeling, road alignment, image classification, or map projection?
Option B, sir.
Okay, road alignment because there we are interested in like we want to just consider a one level of a road and that's why it uses the just single contour extraction rather than a multiple contour showing the same elevation. Sometimes we are needing of just we are putting a gradient or something to a road to get a slope or something, but most of the time it is just situated at one particular elevation value only rather than using multiple contours. Whereas in flood modeling, we are interested in identifying the depth at different how much of area is affected by flood if the flood depth water is 1 meter, 2 meter, zero point 0.5 meter. So for that, this flood modeling part, we need to extract the multiple contours. Similarly, like image classification and move projection, they are not at all application of this contour extraction. So correct answer here is option number B. Next question is a route of constant elevation correspond to ridge line, contour line, drainage line, or watershed.
Option B,
Contour
sir.
line.
Yes, so the correct answer is contour line, line joining the equal elevation. Yeah, next question is which of the following input are required to generate contours? DEM raster, attribute table, polygon boundary, or GCPs, which is a ground control system.
DM raster.
Yes. Z factor is used for changing projection, unit conversion between horizontal and vertical, resolution change, or slope calculation.
Option B, sir.
Yes, so basically it is useful for converting the unit from horizontal and vertical, like basically to make it similar to each other. And can anyone tell me why this is required? So can anyone give me the example of it?
If the undulation is very small, then we can get the better view by increasing the scale. Increasing the scale.
Yes, that is true. But like we can magnify the inundations or we can magnify the elevation area so that it becomes visible properly. But there is a one more reason which we are dealing with. So whenever, like, let me show in my QGIS window so that you will get some more idea. So let me open any, like when you download any DEM from any particular source, the DEM will be in degree. Like if you see the property and then check the unit of the DEM, the extent is like, see, you can see it's 80 to 81 and 29 to 30.22, which means it is in the coordinate system is in degree. The units are in degree, but the value of elevation, which it has as a pixel value, that is in meter. So the X and Y, the size of pixel is in degree, which you can see here 0.000277777, which is in degree. But when you consider the third dimension, which is Z, that is in meter. And because of this reason, like if you wanted to calculate slope or if you wanted to calculate aspect, there we need both the dimension X and Y. So if our X and Y are in degree and our Z is in meter, then slope is like change in rise divided by change in run. Or if run is in degree and rise is in meter, then it will create a chaos because all the units should be proper. That's why we use this Z factor so that we can convert the meter value to degree or degree value to meter. Basically, we'll use a conversion of, if our data is in degree, then we use the try to convert that like meter value to degree. But generally what I recommend here is whenever you start working with any hydrological application or any application related to terrain, where you are interested in doing visualization or cutting, filling, road alignment, contour generation, you better convert your data from a normal, like which is coordinate system which is in degree to coordinate system in meter, so that everything you will be in meter. And if you want to do such stuff in QGIS, for that you have to use the tool warp. So warp is the reproject tool. So if you use this tool and then after you give the DM data, and then after you give the source DM and the target coordinate system. So how will you get to know that which coordinate system it is following? So already we see it's from 80 to 81. So here if we'll go to 44 north, then we can see its extent is from like 78 to 84. So it falls within this 44 north, and that's why we'll select the 44 north here. And then after nothing else, we'll just run the analysis and convert our data from degree to meter. And now if you see the property of the reprojected data, which I have converted into meter, you can see the extent is became the very two big values. So because it has converted from degree to meter, and in the similar way, you can see the pixel size become 28.19 to minus 28.19. So approximately 30 meter length pixels, sorry, SRTM data is there. And that's why you can see now X, Y, and Z, all three are in meters so that we can do all the calculations directly. So that was the reason to provide the Z factor in the multiple tools such as slope, aspect, even contours. Okay, going to the next question. Z factor is always equal to 1. Is it true or false?
False.
False.
Yes. So it can be anything, it's just for unit conversion. So we can set to convert from meter to inches, meter to centimeter, meter to degree, and so on and so forth. So next question is conversion from DEM to points continuous to discrete is an example of raster to raster, vector to vector, continuous to discrete, or discrete to continuous.
Option
Option C,
C.
sir.
Yes, so DEM is a continuous one, and that we are converting into the discrete one. Okay, next question is random point generation is useful for which kind of application? Interpolation, classification, pattern analysis, or rasterization?
Option A, sir.
Yes, A. Anything else? So your
Interpol.
which one?
Interpol.
Interpolation. Okay. So I think that answer is wrong because see, like what I taught you in the class, according to that, it's fine. But generally, if you have DEM, then we are selecting a few point and we do the accuracy assessment and we do the pattern analysis using that. Interpolation is like you are not converting from like DEM to random point generation. Okay, there already you have the random point which you have collected through survey or LIDAR or any topographic survey which you have carried it out on field, either using GPS or any other instruments. Okay, but generally when you have to convert uh, like from points to surface, then this is required like interpolation. Basically, you have the points which are taken using the machines or instruments, and then you are converting from them to in continuous DEM. But here you already have DEM and you are generating some point over it. So now you want to see that what is the temperature at given location or what is the height or elevation at a given locations. And then you can compare that data, what is how the temperature is changing, how height is changing according to different cities or different location, and how they are distributed along some river or how they are distributed in the city, so on and so forth. So that is known as a pattern analysis, and that's why like we do the random point generation as well. Okay. So next question is random points must always lie within the DEM extent. Is it true or false?
True, sir.
Yes, so it should be within a thing, like your extent only. If it is outside your extent, you will not get any point values. So basically, this extent is my like till point when I'm seeing my DEM, not like outside that. So if you want to generate that kind of points, then you have this mm, tools such as if you see in the vector research tools, and then you can generate this random points in extent or random point in a within a polygon, random points in a line, random points in a layer bound. So everywhere you have some bounding thing is given, which means you can generate within that particular area only. So if you consider random points in extent, basically you have to give the input extent. So either you can draw it on map or you can provide it directly. So here I have given the extent of entire map which is visible to me. And if I generate a, let's say 100 points, okay, and like, okay, fine, we'll go with this. So it can be outside also. Now we are not able to extract the values from these locations. So that's why it should be within the extent. It means how the far that DEM is being. So for that, what we do is we go to vector and then research tools, say same thing at the random point in extent. But here, what we will do is uh, that here we will calculate from layer. So there we'll give the like information about the sample DM. So whatever the DM layer we have, just do that for that area only. Or else you can draw on map canvas also. So let's say I want to generate, I don't want to interested in the DM in the edges. So I will do something like this. And then after I am interested in generating 100 points. But here you can see the coded system is in 4326. So keep that in also in mind, because whatever the coordinate system which you see over here, so it will show for that extent only. Okay, so and then after you just run it. So now you can see all the points which has generated it now, they are like generated within this bound only. Again, you can see some points are very near to each other, some points are apart from each other. So to control that, there is one more option which is given there. So you can go to vector research tool and then the same thing, random point in extent, but you can see the minimum distance between 2 points. So you can add that location also. So if you consider the point and the buffer generated to that point, which is from the distance which is given here, it will not have any random point in that particular part. So considering that, it will generate all the random points. So that also you can fix. Now this is about the random thing. Now if you want to generate some points which are like grid wise manner. So for that, what you can do is you can use the same research tool, and instead of random points you can select the vector creation and grid, and then you can write the point. Again, you have to select the extent to which you want to work on. So like if I'm like interested in right now anything else also, I can do that. Like, so I'm interested in this much. Now you have to specify the horizontal spacing and the vertical spacing which is required in the generation of grid, or this is systematic creation. So what we'll do is we'll just write 0.001, and then after we'll just run it. So you will see at the 0.01 resolution how many points have come, and they are very continuous in nature. So if we will extract the data here, it will become a very good DM. But again, when we are constructing it from the natural data, we do not have this many points, and that's why we suffer with the quality of the DM which we have. So this was about the point generation. This is a systematic and having a uniform layer also. Okay, moving to the next question, which is a identification of the correct statement. So the question is like a contour line forming a V shape pointing upwards of upward hill indicates valley. Where statement number 2 says a contour line forming a V shape pointing downhill represents cliff. So which one is true and which one is false?
Option D, sir.
Option D. Okay, anyone else?
Both are false.
Both are false. Okay. So, can anyone tell me that why the first one is false, or why do you think it's false?
It should be opposite.
Opposite of like
Yeah, V shape should be point. If it's a cliff, then it should be pointing upwards, and if it's a valley, it should be pointing downward.
okay. So let's clear it out, because anyone else? Why the first one? What she's saying is true, or do you have any other justification for that? Anyone? I think better idea is like let's just plot the contour, because here I can see a valley and ridge also. So we'll get to know that are we making sense or not. So let's plot the contour. So I will say contour, and I will select my DM. Contour interval, let's say I will select a contour interval of 50 meter, or let's say 25 meter, or let's just go with 50 only, and then just run it. So I got a very good contour lines here with me. Just change the symbology of it. So you can see these are some of the valleys. Okay, so I will change the color of my DM as well, so that you can see this black part which is following through is a river. Let's change the symbology so you will able to focus it in more in good way. Yeah, so this is a typical area, and this is the contour line of it. So now you can see this is a valley. This is also a valley, and this is the ridge line, which you can see it's a top of mountain. Okay, so now we'll see for valley. So valley is what you can see U shape or V shape. Now V shape is pointing toward which area? Higher elevation or lower elevation? Okay, can you see this pointing V shape? And that is showing towards which area? Higher area, upslope area, or you can see it's a like uphill area or area which has higher elevation. So you can see this V is pointed like this, pointing is towards the higher elevation side. Similarly, if we see any other valley, if you see this valley through which the river is passing, that is also pointing towards the higher elevation side, if you notice. Similarly, now if we take some other valley as well, this valley, you can see U or V, which is continuously going towards this area. Similarly here, similarly here. So all of them are representing the same thing, that if the valley is there, then it is a pointing towards the higher elevation areas. And because of that, the contour line forming a V shape pointing uphill, uphill means towards the top, indicates valley. So that statement is true. Okay, and the next statement, a contour line forming a V shape pointing downwards represents cliff. So that is wrong. Why? Because we have seen in the formation of cliff, it's like this. It will cross contours, and it does not like the U or V. But generally, if it is crossing, then it is a feature of cliff. So that's why the statement number 2 is false, whereas first is correct. Did you get my point, everyone? Or any doubt in this? Okay, so if there is no doubt in this, we'll move towards the next question. Elevation values assigned to a point from a DEM are called attribute join, Z value, raster value, or pixel indices.
Option B, sir.
Yes, so correct answer here is Z values, which is not an application of random points. Pattern analysis, statistical comparison, terrain visualization, or sampling.
Option C, sir.
Yes, so terrain visualization is not an exam actually. It's true. Sampling, statistical comparison, patterns, all three are the application of it. Yeah. Moving towards the next, point pattern analysis evaluates elevation, distribution of point, raster resolution, or projection.
Option B, sir.
Yes, so it basically evaluates the distribution of points rather than the other aspects which are given here. Contour line with U, or you can say V also, V shape with convexity towards low ground, means downhill side. Ground indicates valley, ridge, basin, or cliff.
Option B, sir.
Option number B, ridge. So that is true, and like we'll see also why it is true. So let me go to QGIS window. So now reach means, anyone know about what is reach? So reach is a line at the top of the elevation. You can see this line, which is, you can see in the white. Okay, so this line is a like top mountain range line. And you can see now this line, if I will focus at some particular line, so you can see this is a kind of U. Zoom it further. So this line is kind U, and it is going from higher elevation to lower elevation. So this U is pointing towards the lower elevation areas. Okay, and it's a kind of U, convexity towards the low elevation area. Similarly, from here you can see this is like this. So basically from here it will go like this. So I will show the profile also, so you will get some more idea about the reach pattern as well. So I will add this layer into my, and then after, so so you can see the elevation is increasing, and basically it's like U is towards the lower elevation side. So the convexity of this U or V line, that is towards the downhill areas. So that's why it is a ridge. And similarly now if I will see for uh, let's say valley, then you can see it's a valley. So it's going like this. You are going from this to this area. Okay, and this here, the V side is higher towards the, like this V or U shape is higher towards the higher elevation areas. So in case of valley, it is towards the uphill area, whereas in case of ridge, it is towards the downhill area. So if point is valley, if it is going down, then top elevation. If it is a ridge, which is a top elevation, then it is towards the lower elevation. Okay, and here you can see the examples in more detailed way. So this you can see the ridge and valley structures. So these are the ridge, which is going towards the downhill, and these are the valleys which are coming towards the up, which is a uphill side, which is a valley. And now if I will just focus more on, if I will show you in a 3D view so that you can get the more better view of it. Let me show the 3D view of the scene. So we'll focus on this particular part. So here you can see now. And what we'll do is we'll just make it 3D. So for that I will go to configuration. Instead of flat terrain, I will select my BM raster. I will select my layer, and I will, let's see that whether it's visible or not. First of all, yes, it is visible. Yes, so we will not have to change the exaggeration. So you can see now. Now this is a valley. Okay, so valley, this U shape is going towards the upper elevation area. Whereas if you see this ridge, which is a top part, then this U part is going towards the lower elevation areas. And see the other part also of the same terrain. So see again the valley, it's going towards upward, and then ridge, which is going downward. So ridge is going downward. Then again, like if you see these two contour lines are closely spaced, the thing which we have learned, I think I will just minimize this thing, and you can see wherever if we see the contour lines which are closely generated. So you can see here the contours are too close to each other. They have 50-meter only, but they are like you can see is this part where this contour lines are very crazy, like it's very fine. So if you plot the thing here, you will see there is either there is some disturbance which is there or some error in the production of BM. So I will add this layer, add it here. Is it okay? This first. So you can see all of the sudden in just few meter, it's changing too much. So that is a high slope. Whereas here also, if we see this particular part, then elevation is changing much more. And the same thing, if I will plot the same line over here, you can see the contours are widely spaced. So the slope will be very gentle. And here, if you the same thing, if I will plot this to this basically, so you can see the slope here and slope here. Lines are almost similar, but the slope elevation changes very more in this particular part, whereas elevation changes less in this particular part with the same distance we travel in the x direction or y direction basically. So that is the thing, like when the contours are spaced close to each other, then it will show the high slope or steep slope. If it is widely spaced, then it will show the gentle slope. And if it is too wide, then it will show the plains. U shape pointing towards downhill is a ridge line. U or V shape pointing towards uphill, that is valley. Contour line never cross each other, but if they cross, then it is during the overhanging cliff part. So these are the characteristics of contour. Okay, moving towards the any doubt in this contour part? So again, I think there are two more characteristics which are remaining for contour. So how do we decide that whether the given DM is a hill or a lake? So if it is a hill, single hill, then what you will experience there is contours are going like round contour, and they are going up and up. So you can see if any hills or something is not there in this thing. But if it is, see this particular part that are like, yeah, you can see here, it's a round and round. So here what will happen is now we cannot see whether it's a hill or like hill or lake. For that we have to get to know about this area, vertical dimension. So you can see this is a hill in general. But how do we get to know it's a hill? Here the color is representing it. But if we see the labels of the contours which we have plotted, then if we go to properties and then plot the labels, single label, and so now you can see the labels are like 6300, then 6250, 6200, 6150. So as you are going away from the center, these contours are decreasing. The elevation values are decreasing. It means it should be hill only. It's the same thing if you are going towards the center, or if you're going to our, like if you are going outside the center, then if the contour is increasing, then it should be a depression or a lake. But here in this case, it's increasing. So it should be a hill. Okay. So here I don't know, do we have example of lake or not? But I think my point is clear to you. If not, then you just ask the question again. I will repeat. So this is all about contours characteristics. Moving to the next question, which distribution indicates clustering? Equal spacing, random spacing, group point, or linear spacing?
Option C, sir.
Yes, so group point means clustering. Next question is which statistical property is used in point pattern analysis? Elevation gradient, distance between point, raster resolution, or projection?
Option B, sir.
Yes, so distance between points. Next question is, which of the following is not a type of point distribution? Random, uniform, clustered, or linear?
Option D, sir.
Option
D.
yes. So random, uniform, like which we have seen right now, that how to generate a random point and how to generate a uniform point. If the point is clustered towards some location, then it is clustered, and if it is a dispersed or it's kind of similar to random, then it's considered as a clustered or dispersed, random or uniform. So linear is not a type of distribution. Next question is, uniform distribution implies equal spacing. True or false?
True, sir.
Yes. Next question is, mosaic of DM is required when data is missing, area spans multiple tiles, resolution changes, or projection mismatches.
Option B, sir.
So area spans multiple tiles. Yes. So if the same area, if it is being covered by 2 or more tiles, then we have to make a mosaic of the DM to get the seamless view of a given area. And that might be problematic sometimes when the acquisition time is different, or the sunlight conditions are different, or if they have clouds, then it becomes very difficult to make a seamless mosaic. Okay, so next question is, a 1 degree DM tile roughly covers how much area? 10 by 10 kilometer, 50 by 50 kilometer, 1110 by 1110 kilometer, or 500 by 500 kilometer?
Option C, sir.
Yes, option number C. Mosaic operation does splits rasters, merge raster tiles, converts raster to vector, or resamples raster.
Option B, sir.
Yes, so answer is merges the raster tiles. That's what the mosaicing means. Next question is, if contour interval is constant, increasing with increasing density of contour implies decreasing slope, increasing slope, constant slope, or flat terrain.
Option B, sir.
Yes, the correct answer is increasing slope, because contour interval is like 10 meter, 50 meter, which is a similar, like how the elevation is changes at every 50 meter up. So if they are near to each other, it means what? That like the elevation is changing very rapidly, and then you, because of that, you will see like quick change in the elevation values rather than the slow change. If the question here is decreasing density of contour, then it will say the answer is a decreasing slope. And if it is a constant, like if it is at equal spaced distance, then it is a more or less constant slope. And if it is too far away from each other, then it's a flat terrain. Next is, so I think this thing we will see here, like relatively flat, because this area is hilly area, so we'll not able to see the more thing here. But yeah, if we like plot the same contour for this DEM at, let's say, 200 meter, so what we'll get is very good view of this thing. So now you can see these contours are very widely spaced. So in relative sense, when you see this, like every contour is at a 200-meter interval. So here the contour lines are densely spaced, so it is changing very quickly. But here it's a very widely spaced, so slope is changing very slowly. Or you can say this is relatively plain area, whereas this is like kind of slow change, like sorry, a gentle slope, and this might be a very steep slope considering the 200-meter elevation. And this is all about relative, because this is a like hilly areas, so you might expect a lot of elevation change. But in the same way, if you make it comparison with some plain areas, then you will get a very good perspective about this thing. And here you can see also the good thing is this V shape towards the uphill side, then U shape toward downhill side representing reach very clearly, considering the because elevation difference is too much here from 2270 to 6887. So earlier the contour density was very high, and that's why it's like good to be visualized. But yeah, sometimes it's if you just get a coarser view as well, you will get to know more about it. Okay, next question. Major challenge in satellite image mosaicing is resolution, date difference, projection, or file format.
Date difference.
True. Next question is seamless mosaic means same projection, no visible boundary, same resolution, or same file size.
Option B, sir.
Yes, so no visible boundaries. Overlapping DM areas can be handled by ignoring overlap, keeping the first dataset, blending value, or deleting pixels.
Blending values.
Yes, blending value, that is a one point. And then I think we can do blending means we can use mean, median, or any other statistical measure, and we can do the blending. In addition, we can also do something like this, that keeping the first data set or keeping the last data set or keeping the like median data sets or keeping the data sets when there is a less cloud cover or no cloud cover. So we can do that as well, and blending of values as well. But there is no point of deleting it, because then we'll completely lose the information when there is an overlapping part. And ignore also we cannot do. Basically, ignore and delete both are same thing. So we cannot overlook into that. Next question is, which of the following indicates a depression in contour map? Closed contour with increasing elevation inwards, closed contours with decreasing elevation inwards, parallel contours, random contours.
Option B, sir.
Yes. Next question is, clip or extract operation requires raster only, polygon and raster boundary, line feature, or point feature.
Option B.
Yes, so it requires polygon, basically through which we want to cut, and raster, what we want to cut. So it requires polygon and raster both. Next question is, clipping a DM produces a new raster subset, vector file, table, or image.
Option A, sir.
Yes, so it's a subset of another part. Clip operation works only for raster data. True or false?
I think
False.
false.
We can do it for both raster and vector. Which cannot be subsetted? Raster, vector, tin, or polygon?
Teen.
Tin, because tin is a triangular faces. So if we will cut it using something, we'll lose the information from that triangle part. And that's why it will become some other polygon. That's why it's not possible to subset a tin data. Next question is, a watershed boundary is an example of point, line, polygon, raster.
Polygon.
Exactly. It's a line, but it's an enclosed line, which will create a polygon. First order DEM derivative includes slope, aspect, hillshade, curvature.
1, 2, 3, sir.
Slope, aspect, and hillshade. Curvature is a second order derivative. Second order derivatives include slope, aspect, elevation,
B
yes,
and D.
curvature and flow conversion. B and D, okay, contours, true. Okay, so I think second order, okay, contour is a first order only, it's a flow conversion. Yeah, so I think I will show you the total list only for this. Let me show the thing. Let's say, so I think within the fourth week class. Okay, I think it's in first. So basically those who get it easily, such as slope, elevation. Yeah, so this the first order derivative of DEM is like slope, aspect, hillshade, contour, and point, right? Which we'll get very quickly if we have a DEM in a projected coordinate system. So slope, aspect, hillshade, contour, and point height. It are a first order derivative. Then second order derivatives are curvature and convergent and divergent form. Flow. So that also we have studied the different type of curvatures, surface curvature, total curvature, profile curvature. So based on that, it will decide whether the water is accelerate or decelerate or convergent or divergent will happen. So that are the second order derivatives. Then the third order derivatives, which are the drainage network, watershed boundaries, which are the processed, like ones will calculate the slope, then flow directions, and then we'll get the drainage network. So that will be the third order derivatives rather than a second order derivatives. So drainage network, watershed boundary, topographic position index, wetness index, sediment transport index, and view shed. So all of them are the third order derivatives. Okay, so yeah. Next is third order derivative does not include drainage network, watershed, TWI, or aspect.
Option
Aspect.
4.
Yes. Hillshade is a first order derivative. True or false?
True.
Yes, so that is true. Yeah, so next question is which derivative is used in hydrological modeling? Drainage network, TWI, sediment transportation index, or all of the above?
All of the above.
Yes, so we can use everything. Okay, so with this, we finished this quiz. And okay, so now I think we are closer to the end of this course. So anyone has any questions for this course or this previous lecture or week 11 videos? Any questions on that? So particularly from this part. Okay, so if you have any questions, please unmute and ask. If not, then I think we'll see some of the other thing as well. Like basically some site from where we can download the data sets, and then after we'll do hands-on in QGIS. So first of all, the sites which I want to show you today is that site name is ResourceRat or Research Watch. So resourcewatch.org. So like I just oh, you can see on the top they have shown the contour lines. Okay, so yeah, anybody wants to ask anything? Okay, fine. So now the site is actually anyone has asked anything or something? But I just was where I can get the practice questions. Okay, so regarding the practice questions, like in the NPTEL, like I have provided the like 50 around 40 to 50 questions for each week. So in addition to the 10 questions which you have in your assignments, you will have around 50 questions for all the week. So that can be accessed from the NPTEL only. So in NPTEL, if you go to this, like I think it's visible. Uh, so if you go to this problem solving session, January 2026, and then if you see the problem solving session recordings, you will go and get one link of one Excel sheet. So in this Excel sheet, if you go and you can go to this presentation folder link. So I have uploaded all the question answers in a form of Google Microsoft Forms, everything here. And once we finish this course, I will put the PDF with question and answer again as a PDF format in one of the sites, and I will upload the same link here only in just upcoming week. But yeah, before that, if you are interested, you can just go to any Google form, Microsoft form, and then you can attempt questions which are for practice. So it will give you a good practice of all the week's content before your final exams. Yeah. Okay. Yeah. Apart from that, I mean, what you can do, which I think is good idea, is that you give your all the content of all the classes to ChatGPT or any other AI tool, and you can ask it to create a random 10 questions, 20 questions every day for you, so that you recall the concept which you have learned, or you can just modify the workflow in such a way that ask it to give you questions every day or every week from every week before your exam, so you will get to learn more and practice more and more the thing. So that also you can do. Yeah. So what I want to show is the research watch site. So here there are lots of things which is for energy and pollutions happening across the world. And there are a lot of data, GIS data, which are available here. Even near real-time data are also available. So I will just explore some of the data sets which are available on this particular site. So here, I mean, you can just first of all, you can just see which topic you are interested in. So basically, if you are interested in the data sets of, let's say, food and agriculture, so you just click on that particular dashboard or tab. Now you will see the employment in agriculture. So how much employment? So this data is aggregated at world level. So you will get the world view. So this is the GIS data, which is employment in the agriculture sector, and you can see the visualize the data also that in India around 41% employment is from agriculture. If you see in the Ethiopia, then 66% is from agriculture. Similarly, if we see the Mozambique, and then 71% is from agriculture, and then similarly, like we see here the Laos area, then 63% area. If we see in Iran, only 70% is from agriculture. So yeah, this is the thing. You can download the dataset as a shapefile format, and you can use it for your own purpose. Similarly, if we go back and check the datasets which are available on this particular platform, so you have cropland and pasture area, how much cropland is there in the different grid cells. So basically, it's a gridded data. The earlier one was vector data, but this one is a gridded data, which is in the form of raster, and this is collected over during the year of 2000. So you can see here the 2000 cropland percentage of grid. So in the given grid, how much area is a cropland area, and everywhere, like if you go to the grid and you can just click on it, and you can just get to know about the as well. Similarly, I mean, same thing with the pasture area, and the cropland mask is also there. So where the cropland is there, so that mask, whether the cropland is there or not, so that mask is there. And then pasture land, how much pasture lands are available, so that thing is also available. So this is the pasture lands, so around like in India like less than 20%, but if you see in the China or in the Africa, you will see a lot of pasture lands available. Similarly, these data are for cropland. Similarly, maize, rice, soybean, and wheat yield and its trends are also given. So it's a grid-wise format from 1989 to 2008. Then, if you see here again, then the vulnerability, conflict index, food price spikes, how it is happening, oil palm connection, air quality of nitrogen oxide, black carbon estimate, and there are lots of things which are available and all are available in GIS data and ready to download. So that is regarding food and agriculture. If you go and check out some other tabs which are given here, uh, such as global power plant database. So this will show how many coal, oil, gas, hydropower, nuclear, solar, waste, wind power, and also other. So if you see in the coal power plant in India, so you can see all the black ones which are showing here, and yeah, you can change the base map also if this is not looking proper to you. You can just make a light color base map, so you can see all those are the coal production power plants in India and its capacity by megawatt. So now if you see the size is representing basically it's a capacity. So if I click on any of the particular thing, so it is around 1200 megawatt, and that is a coal power plant. But the interesting thing which you can see here is like if you see this part of China around this Mekong River and its delta, like this part, then you can see a lot of hydroelectric power plant. But here in India, like majority of the time, we have a coal power plant, and then it's dominated by the oil and solar. So this orange one, this which you can see here, are a solar plant. So you can see this area of Andhra, Bengaluru, like it's a highly developing a majority of the solar. Similarly, we see in the Rajasthan and the Gujarat, like Kutch region. So they are having a lot of solar power plant. Then this part of the around UP, Chhattisgarh, MP, they are having majority dominated by the coal power plant. Some of the western parts where we have sudden change in the elevation, they have a hydroelectric power plant. Here also we have hydroelectric power plant, and in the upper part where we have the high mountainous area of Himalayas, we also have a hydroelectric power plant. And similarly, few nuclear plants also you can recognize from this particular part, that NAPS nuclear power plant. Then one power plant in Mumbai, which is nuclear power plant, is in Mumbai, which is also in 1400 capacity. But the thing is, you can see this partially, which part like this along this river, China is producing a lot of hydroelectric power plant, and this is the Three George Dam, which is a kind of biggest dam, and you can see the how much 22,500 megawatt production it is doing it from just one single site. And here also you can see the amount of energy which is it is producing, which is far like bigger than the coal or any other production power plant which you see in India. So the efficiency or the output which is they are getting from one side, it's quite high. And you can see along this coastal line they are having a lot of coal power plant as well. It's not just renewable, but they are also extracting a lot of coals, which you can see by this highlighted black color. And then solar in this particular part is also being thing. And then along this, like like in the southern South Korea and Japan, you can see the lot of nuclear power plant as well. Similarly, if we see the gas power plant that are also located here, and then some of the wind power plant also. Now you can see this is the purple color. So this is the oil and gas area, which is quite popular right now. So there you can see a lot of gas power plant which are being there. So it's a global energy distribution, and you can learn a lot like how this energy transitions, energy flows are happening, and then you can analyze a pattern and then draw a lot of conclusions based on that. Here you can see a like hydro and wind power plant sites. So similarly, if you see in US, majority of them are gas power plant. If you see, then coal, and then again hydro and wind, and some of the areas they are producing a solar also. But the distribution is quite heterogeneous rather than focusing on one. Even in India, majority looks like a coal, but we are coming with a different like variability of the different fuels, but there is a need to do a lot of transitions getting a green and renewable energy in this part, because UP, Bihar, Chhattisgarh, Jharkhand, there is high need to do these things to produce and find the other source of renewable. Because see, if the most of the energy is coming from coal, then at the some point, if we want to go for a renewable, then we have to export energy from some other, like like we have to do the import from the other states, and that is not viable. So that it's better to start a plants which are renewable in this area as well, to get a cleaner and green energy for the utilization purpose. Yeah, so this kind of data are very good to analyze, and you will see a lot of data regarding the resources which we have on earth on this particular sites. So these are the couple of data sets which I've showed you, but yeah, there are a list is very limitless. You will see air quality data, plastic input from river to into oceans, endangered species and critical habitats of world. So if we see in India, which are the so if we see in India, so area which is showing the extinctions. So this data is not available. They've given these sites. Yeah, so site names they are given. If we see here, so Kudre Muksh National Park, then few in the southern part, which is Kalakad, Mundathurai Tiger Reserve. So this is endangered species data sets. Then we have a lot of other data sets as well, such as air quality data are there, aqueduct, baseline, water state, global material flow, how the material flow from each country, like one country to another, import exports happen. And then few near real time data sets are also available. So there you can see the data sets of earthquake which are happening from coming from USGS. So if we see the 4/7/2026, basically the today only. So what we see here, like when this earthquake happened today. So you can see this is highly actively, this is known as ring of fire region along the Pacific Ocean, and then you can see a lot of seismic activity happens here, and less than 5 magnitude earthquake happened here. And if you see here, like this is also a highly seismic zones areas, and you can see like you will feel the magnitude of 4.6 very, it's a very like in routine, like you'll see a lot of earthquakes which are being happening here at this particular locations because of this high uh, earthquake prone areas. So that is thing, and then there are a couple of dashboards for energy, forest, ocean, food, society, climate, cities, water, which are available. So I mean, I think we cannot cover everything in this class, but yeah, I've showed you this site, and then wherever you are interested, you can just go to this site. If you are interested in some of the data sets, you can just go and check it out. So this is the data sets regarding the urbanizations, how it expanded. The urban growth is expected through the mid to um, so you can see how it is going to be affected. Urban is going to increase while rural is become stagnant, and it will go down also, rural populations. And then if we see in India also, area under the growing and we are projected to further grow. So the thing is, let me zoom it. I think if we can do and check. Mm, yeah, so infrastructure investment, how much it is happening, housing, clean water, sanitation. So everything you will get like vectorized data set which you can download. This is not coming. So now I think if I will click at some location. So these are the urban area and the probability of the urban expansion. So where it is the chances of that it will get expand and how it will become the conglomerate regions. So that thing is also given here. And then couple of other things that categorization, struggling city, emerging city, thriving city, and stabilizing cities. So there are clear geographic trends in the how prepared cities are to meet the growing needs of the residents. So whether they are struggling with their needs. So like in India, if you see, there are most of the emerging cities comparing to few which are the struggling cities. So let's see like which of them are the struggling cities basically. The one which is here. This data is not okay. It's I'm not able to get the idea. Okay, but yeah, you can see the struggling cities here, like thriving cities and stabilizing cities. So you can like read more about this thing here. So I think we'll not waste the time to see this. Road traffic death rates, water intake locations from where they are taking, um, like extreme precipitation events which are prone to projected, floodings, droughts, water shortage, productivity, economy, temperature, suitability, land cover, and so on and so forth. So we'll not go into this detail of this. But yeah, so this is all about this particular site, which gives a tremendous amount of data sets in the vector and raster format, which you can download and do the analysis. I think with this, we can conclude this particular session of data downloads. And now I think we'll go to the QGIS. I think any doubt anyone in this particular site? So I think you can explore the data sets more out there. Uh, Now I think we'll go to QGIS and do some analysis. So I think before going to that, we are going to do a hydroshed analysis, like basically water analysis. So for that, I will give you some of the brief that how do we conduct this kind of analysis, what is watershed, which we use generally do for hydrological purpose. So here, the thing is, we are interested in delineating the watershed area. So first of all, the question comes to our mind is like, what is watershed? So answer is a watershed is an area of land from which is from where all the water is getting like collected and it is going to one single outlet point. So this area is also known as a drainage area, catchment area, upslope area, catch or so on and so forth. So here you can see this is the point where all the water is coming and this much portion is responsible for collecting water from this location. Now, if we see this is the major river basins which are in India. So you can see here the Brahmani here. Then you have a Brahmaputra. Then you have Kaveri at number 3. So this is a Kaveri. Then you have East Coast. Then you have a Ganga. Then you have Godavari. Then you have this Godavari. Then Indus. Then you have Krishna, which is number 8. So Godavari, Krishna, Kaveri, then this is the west coast, Sabarmati, Indus, Ganga, Brahmaputra. Then you have here as a Subanrekha, Brahmani, and then you have this Mahanadi, and then this will be the coast. So this will become your northeast coast. Then this 4 number will become east coast. This 18 number will become the west coast. Then 15 number will become the south coast, and this is the Sabarmati River Basin. Okay, so this is the how the like major river basins are divided in India. Uh, then after, if we see why there is a need to do it is, so we are interested in timely and effective water resource management, irrigation management, flood and drought risk evaluation, and scheduling the releases, and so on and so forth. Edit which scale we are interested in, whether we want to see what is happening at hourly scale, daily scale, monthly scale, or even at longer than that. So this depends on for what applications we are using it for purpose. If we are interested in a flash flood study or the urban floods, then we can go with the like or the sudden downfall of the like cloud burst and all. So that time hourly data is necessary, but if we are considering the long-term flood, droughts, then daily is also necessary, fine. And when we are interested in the planning of irrigation, demand, scheduling, and that kind of thing, then this monthly data is useful. And when we want to predict how much water I'm going to use it for the irrigation purpose in the next year, how much water I have to store in a reservoir and such thing, then you will use the seasonal data sets. So this is a temporal scale at which you are doing the modeling. And the same way, at which area you are interested in. You are interested in the national level study, or state level study, or the basin or sub basin level studies. So according to that, you will focus on at which scale you want to do the analysis. So once you want to do generate the thing, so this is the same DM which we have just used in our QGIS during the question answer. So basic idea here is this is the outlet point where I am interested in generating a like how much area it will contribute. Now what the thing is let me my pen. Yeah. So basically, see if you see the clouds here, or let's say here. So if these clouds are raining like this, so if the rain will happen in this area, which is within the black part, then and then the water will come here. If the rain will happen here and some water is falling here, then the water will go there. Water will go here, but it will not affect here. So how much area is contributing to water at the given location? That is the catchment area. And why do we need to create this kind of catchment area is because let's say we want to construct a bridge here. So we have to find out how much water will going to pass through that bridge from the under the bridge, or if we are constructing a check dam or a dam or something. So we want to store a water. So we'll get to know that how much water is coming to this location. So for that purpose, we need to find how much area it is contributing. So once we get the overall rainfall over the area, then we multiply it with the catchment area. Then we'll get the on an average flow, how much flow it can generate. So let's say if this area is receiving 100 mm or 1000 mm rainfall every year in an average, and the area is let's say 1 square kilometer or 10 square kilometer, then we can just do the convert the kilometer square into mm, or our rainfall into meter, or basically then we'll convert everything into meter cube. So then after we'll divide it by 365 because we have annual data. So we'll get on an average this can get this amount of volume. So when we decide the reservoir, we'll keep the capacity of reservoir according to that. So height will be determined based on that, how much water it is coming and how much we want to hold it. So there are the other factors also associated here, that how much water we need actually for depending on the different demands, such as the irrigation demand, urban demand, or atmospheric demand, health like river demand, because we can to keep the natural flow. So based on that, we'll decide the sizing of the reservoir height and the like area. Uh, and then after once we finalize where we want to construct a DEM, first of all we'll collect the DEM data of the region. Then after we will, so that can be done using the open topography or the sites which we have showed you in the previous classes. What you have to make sure is that whatever you are downloading, the units are in degree. So you have to convert that unit from degree to meter first of all using the rep tool. And then after, the thing is it should be always in projected coordinate system so that you do not get any error. Then after we have to do a pre-processing. So why there is a need to do pre-processing? Because some of the data sets will look like this. So now what will happen when we'll do the modeling, that what should pass from here to there, then here the sink is there. So water will not able to move beyond this point, and it will act as a sink. So its sink is like every water will come here and will go and drainage like this only, it will go in a sink. But this is not true. Once this depression will fill, it will flow. So this thing we have to fill first of all. So that is a pre-processing tool which we have to do. And that is being done by the fill sink algorithm. So I think we'll do this thing simultaneously in QGIS also, so that you will get a sense that what I'm talking about. So first of all, I have to convert my dm to degree to meter. So that we have already done while doing this contour. So for that, I will use the tool warp reproject. I will give my dm input coordinate system. So basically here I will give my original dm, which is in 4326 coordinate system, and target is in 44 north. And then I will just run this. So it will give me the reprojected dm in which the units are in meter. Once the units are converted into meter, I will do the second step. I will fill the dm or do the pre-processing so that there will be no sync. So for that, I will use this sync Mang in lieu algorithm. And there are multiple algorithms which are available within the QGIS as well as in the RGS window. So I will select my reprojected DEM here, and it will generate the three output: field DEM, flow direction, and watershed basin. So if you want to save, you can save it using this tool 3 tool. But right now I don't want to save it. I just want to save, like, make the output as a temporary output only. So I will just run this thing. So yeah, so we got the field DEM and flow direction. So these are the flow directions. Now, and flow direction, I mean, you know that -1 represents the flat area and 0 to 7 represents the 0 means north. So that I think thing will learn. So once we fill the thing, then the next step is the flow direction. So 0 means north, 1 means north east, then southeast, southwest, west, northwest, and -1 means flat. And then you will get to know about this kind of raster layer which will represent the flow directions. Then after, you have to see how much area it is accumulating. So if I consider this pixel over here, then it is getting a water from this pixel as well as from this pixel. So the water is getting accumulated from two different points. So that's why the accumulation which is written here is 2. Similarly, now if I consider this pixel which is written 5. So if I consider this particular pixel now, then if I see how many pixels are contributing. So 1, 2, 3, 4. So this 1, 2, 3, 4. And then after, let's say, which one? So this pixel is also. Okay, so this is going here. And then after it is coming here. So 1, 2, 3, 4, and 5. Okay. Similarly, if I will say like this point. So that is 1, 2, 3, and then we have, I think, so 4 now, 1, 2, 3. Oh. Okay, so basically it will do like this. If we see here, there is no point of water is just coming in. So that's 0, then 1. So here only 1 pixel it is coming in. Here also 0, there no point is coming in. Here the 11. So sometimes it will accumulate also. So from this 8 plus 9, 10, 11, like that it will also do. So they will find this flow direction and then flow accumulation. And then wherever we have highest accumulation, we will see the right click and coordinate the copy, paste the coordinates X and Y location. And then after we'll use this upslope area tool where we'll give the X and Y coordinate of this location basically. And then after it will generate this watershed for that particular area. And here we'll select deterministic 8, which is the conversion method, like 1, 2, 3, 4, like this, which we have just talked about. So this direction we will consider 8. And then after it will give me this kind of catchment area. So here, I mean, I will use the another tool, which is a channel network and drainage area. So I will give my field DEM now, and then it will calculate the flow direction we already done, so I'm not interested in flow connectivity, Staller order. So this is the river order, I think we'll do that. Channels we are interested in, basin I think we don't not interested right now, and we'll just run it. So you can see I got various river network like this and Staller order. So Staller order is from -3 to 6, which will show the how dense the river is and which is the primary river and which is the secondary river. So the color with the bright color is the major rivers, like it is connecting water from more than six bound, like six tributaries like that. So it's like if two are merging, so initial will have a value 1, then when they are merging, the next one merged one we have 2, and if they will meet, if 1 and 2 is there, then it will get 2, but if 2 are getting, so it will become 3. So like that it will construct the Staller order. And then after, if you see, this is the how the river network looks like. And then now if I'm interested in finding the like catchment area at this location, like how much area is contributing at this particular part. So I will first open the upslope area tool. So I will see this upslope area tool. Now I have to give the X and Y coordinate here. So I will select the coordinate here. I will copy the coordinates. X coordinate I will give. Then I will copy paste it. Elevation will keep the field EM. Method as a multiple flow direction instead of will keep deterministic 8. And then after we will just run this analysis. So it will give me how much area is contributing at that location. So you can see this is the area which is getting water from the target point. So then after that I can convert, this is a in terms of raster. So if I need a boundary of it, then I have to convert that from raster to vector. So I need a conversion. So for that I will go to raster conversion from, I just want to make it polygonize. So I will use polygonize. I will select my layer, which is a upslope area, and then after I will convert that into vector layer, because the layer which I got from that analysis, that is a raster layer, but I need a vector layer. So I will use this tool. And then after it has converted into raster to vector, and we can see the attribute table of it. Now you can see the DN is 100 minutes, it's just had. And now if I want to add the like how much area it has, I can add that. I will just create a area column here. Instead of that, I will write decimal number. I will write $area. So that is in meter square. So I want to convert that into kilometer square. So I will divide it by 10 to the power 6. So it's around 173 kilometer square area. Similarly, I can add a perimeter, how much perimeter that catchment area has. So perimeter, again decimal real number. So if you don't know, you can just search here perimeter. So length or perimeter. So you can just use perimeter. Again, this is in meter. So to convert that into kilometer, dividing it by 1000. So I got the perimeter and area, both the things. So you can get those kind of feature related to the watershed as well after. So what kind of like that is a generalized work and drainage, and then you can generate this kind of map. So like how to prepare a map that we already discussed, but you can prepare this kind of basin parameters, basin shape factors, drainage network pattern, the Staller orders. So which you can see here that how beautiful this map looks like. So these are the geomorphological analysis or of any basins which you can take. So the major two parameters which are known as basin parameters are basin area and basin parameter, which we already calculated. Then you have basin length. So that is 1.16 area into point power zero point 0.6. So you have an area, you put this thing into this equation, you will get the basin length and total length of stream. So that you will get like from like if you have the vector file of this area, you just find the length line of every line and then do the sum. So we will get the total length of stream. If like more is stream, that it's more denser. Then there is a basin shape factor, which are the form factor, circularity, elongation, lemniscate ratio, and asymmetric factor. So that can be calculated. There are second order derivative of basin parameter. So you use area in the perimeter and the basin length, and then after you can find out the other shape parameters such as form factor, which is a divided by lb, which is a basin length to the power 2. Similarly, circularity ratio, so 4a pi divided by p square, which is a perimeter square. So this parameter will define like how your basin is look like, whether it's a like long one, it's a circular one, it's a fan shape. So depending on that, if it is a like a too long, then it will take time to reach to the outlet point. If it is a fan shape, then also it will take time, but depending on how much density it has. So using those things, you can analyze how much water it will take, like time it will take to travel from water from one point to another point. And then there will be other thing, which is the time of concentration and other hydrological parameters, which you can calculate. If you have LULC, then you can use the runoff coefficient and you can find out how much water it can generate on an average if we consider the runoff ratio considering that particular part. If we have done the deforestation, urbanization, how it will affect to the runoff which is it is producing. So those answers which we can give from this kind of analysis. So these are the some of the other ratios: bifurcation ratio, drainage density, stream frequency, drainage intensity, length of overhead flow, and which you can calculate from this using attribute table. Okay, so that's it from terrain analysis, like which we need for hydrological. This is very initial analysis. Once you get this thing, then you download the rainfall and other data sets for this particular polygon. And then after you just do the analysis regarding the hydrological water balance, stream flow generation, or so on and so forth, which you are interested in. Okay, so this is all about hydrological analysis, which we can do in QGIS, and this is just a basic part of watershed area delineation, which we will do for any applications. And in the previous first week, we have covered one site which is known as MG Hydro. So this site does like you just put a point where you are interested in generating this watershed, and it will give you that watershed just in a few minutes. But if some case, if that is very smaller scale, then you have to use the QGIS for developing that thing. That is good when you have coarser resolution data. Similarly, there is a site known as a hydroshade, which also gives this data of watershed and all, so that you can also decide like download directly from their website, which is a hydroshade data set. So I think with this we'll cover end up this up. If you have any questions, we can discuss that now. So that's what I want to cover for hydrological analysis. Now, if you have any questions, we can discuss that. So I think now only two lectures are remaining. One is in next Tuesday, and then after we have some one extra session that you will get notified, which is on Saturday. So during that particular class, I will cover like gate questions, like questions which are asked in gate geomatics question paper from GIS section. Um, so that I will cover on Saturday on 11th of April. You will get the notification regarding that in NPTEL, but that is will be going to conduct during the afternoon session on 11th. So please join that if you're interested in GATE examination of geomatics engineering. You will get a more clarity of the questions which can be asked from this question, because it will cover around 30 to 40% of the entire paper. So we'll see that on the Saturday, and then in the next week we will conclude this and we'll see the last week questions, some sites and some analysis, as we do always. So if you are interested in covering anything which you think I should cover, then please let me know. I will be happy to do that. But otherwise we'll go with as we go in the other classes. So if you have any questions, then we can discuss. Otherwise, I conclude this session here. Thank you everyone for joining. So I'll wait for 1 minute. If you have questions, please unmute yourself and please ask. Or you can write in chat box also if you're having issue with mic. So I think if there is no more questions, then I will conclude this session here. Thank you everyone for joining, and we'll see you in the next week. Thank you. Good night. Have a nice day. Bye bye.